Hi, my name is Gary and I'm going to be talking about ESTEST, the framework for the verification and validation of electronic structured codes that has become much more in the years since we last presented it at APS in Portland. It is generally known that there is a trove of simulation data being generated by researchers and groups around the world hidden behind publications and results, and there is a sense that if we could access this data easily, consistently, and using modern technologies such as the web, then we would gain more from the collection than as individuals. To be sure, some of this data is solid, and some of it is erroneous. ESTEST began from the perspective of verification and validation on electronic structured codes. But by having and developing this framework, we've come to realize applications in comparison, collaboration and sharing, analysis, and presentation that were very difficult to do without a framework like ESTEST. In this talk, I'm going to be reintroducing the core concepts of ESTEST and what makes it function as a verification and validation framework for electronic structured codes. I'll then discuss our recent work to extend the capabilities of our framework to support scientific research. I'll discuss our distribution model for ESTEST and show you how you can obtain access or set up your own ESTEST server. And I'll conclude by showing how you can discover and share work being done with ESTEST all around the world. This slide is showing you an overview of the core components of ESTEST. ESTEST begins with the input and output data generated by electronic structured codes, such as QBox and Quantum Espresso. These I/O files are processed by custom translators written in Python that take the raw I/O of electronic structured codes into the Unified Representation XML format. Documents in the URXML format are stored in an XML database and XQuery midend provided by ExistDB that can then be served to any web application or other tool capable of XML processing. In a bit more detail, the translators are highly customized to the specific codes they parse while still being separate from the codes itself by working only with the I/O. Currently, we support translations from QBox, Quantum Espresso, Abinet, The Exciting Code, and Siesta, with planned support for more in the future. The Unified Representation format has a simple XML schema that, among other things, stores and reproduces the original I/O of the electronic structured codes, standardizes units and conventions, and represents publications as well as simulations. The URXML schema is still evolving to meet the needs of the codes and the science we would like to represent. With XQuery and the capabilities of XUpdate, it is entirely possible to upgrade any URXML document to a newer schema seamlessly and also reproduce them with better versions of their code translators. Just within ESTEST's core web components, the ability to search, collaborate, analyze, and manage documents represented by URXMLs across servers is supported. The best way to understand these features is to explore our website estest.ucdavis.edu and register for an account. So just within ESTEST's core framework, we have the open database of consistent URXML documents representing simulations as well as publications. The framework we built supports searching, viewing, sharing, and comparing these documents in some simple but powerful ways. The question now is there more we can do with this collection of data and framework of technologies to support scientific research? The first part of our answer is the implementation of ESTEST plugins that extend to specific scientific applications. So far, we have been treating the data collection of URXML documents all together with comparisons and analysis that work on most any document. But what if we add the implicit knowledge a researcher possesses about his or her data subset and develop tools working for that researcher specifically? That is the idea of plugins. Treat problems in a specific domain with implicit knowledge about how the data is organized to produce custom applications. Plugins are designed to be simple to implement using pure XQuery, that is the natural language to transform XML data, and anyone writing their application can also contribute it back to the community in an open plugin development pool. Here I've listed some of the plugins we've already developed, and in particular I'll focus on two of them. Interaction energy is a plugin that calculates the energy difference in binding between a compound and its unbound components. We use a set of ordered URXML document triplets that record the total energy of the compound and its two components to calculate the interaction energy. The other plugin we consider is an advanced visualization plugin for band structures. In plots of the band structure itself is sampled from lines connecting high symmetry points that are usually entirely different from the uniform sampling grid of k-points. We assume a simulation possesses these symmetry points and develop a plugin to recognize them automatically and produce a plot that is fully labeled, colored, and interactive. So in the next 2 slides, I'm going to show you examples of the work we've done with these plugins. But before I do that, I'll just say that the following figures and tables were generated using these plugins and with the ESTEST framework behind them in typically less than 1 minute. So our band structure plugin makes use of the work of Sedwayan and Curtorolo and implements from their paper 198 symmetry points among 14 Bravais lattices and 6 lattice variants. Our plugin can match k-points found in a simulation automatically with these definitions and requires the user input only the simulation itself, the lattice type, and the sampling path. From these pieces of information, we produce a fully labeled interactive plot of the band structure or overlapping band structures for comparison in a JavaScript visualization. Here we see 2 examples of silicon. In the right hand, we have a single band structure for silicon with detailed information about the energy eigenvalue levels. In the left hand, we have a comparison between 2 simulations of silicon band structures using Qbox and Quantum Espresso, and so we can do the comparison and see at least qualitatively that we are matching very well, except for perhaps the highest conductance bands. Moving on to our work with interaction energies, we consider the S22 dataset compiled by Jurika and his colleagues in 2005 that contains 8 hydrogen-bonded complexes, 7 dispersion-dominated complexes, and 7 mixed hydrogen-bonded and dispersion-dominated complexes. For our experiment, we wanted to verify that 2 different codes, Qbox and Quantum Espresso, using the same pseudopotential and parameters, would produce nearly equivalent interaction energies. So we ran the simulations with the compound and its 2 components, 3 per data set, or 66 per code, and 132 simulations in total. Our results did indeed validate the agreement between Qbox and Quantum Espresso, as you can see very plainly here by the side-by-side tabulations of the output of the interaction energy plugin for 22 datasets in the consistent units of kcal per mole. The largest absolute error was 0.03 kcal per mole, and for 13 systems, the error was less than 1 in 100 kcal per mole. From these 2 examples, I hope to have given you an idea of the efficiency gained from using plugins that are completely automatic to handle the post-processing that was once manual and laborious for a researcher to complete. And these plugins are completely extensible and applicable to many other systems that can be reused over and over again. At this point, I want to share with you our distribution model for ESTEST. Our philosophy is that any individual group or institution can set up their own ESTEST server and connect to a wider network of servers capable of sharing data. Data hosted on some ESTEST server can appear in the search results and can be compared and downloaded with the results from other servers, all in one user interface. So far, we have interest in establishing ESTEST servers from Cornell University, Lawrence Livermore National Labs, Lawrence Berkeley National Labs Molecular Foundry, and recently at CCAM they have deployed a working ESTEST server that can be accessed at estest.ccam.org. So having refreshed an introduction of ESTEST framework and talked about our recent efforts to extend research capabilities using plugins, I'd like to conclude with something for the users and potential users of ESTEST. We're launching a new website called ESTEST Discovery that is intended to showcase the work being done with ESTEST around the world. This is the place to tell the story of your research. What did you want to investigate? What were your methods? And have results all supported by data hosted on an ESTEST server and presented with visuals and tables produced by ESTEST plugins. This website is designed to be a collaborative authoring platform. You can register to be an authenticated author, and write your own articles to present your own work. Or if you'd like to host your work instead by yourself, just send us an RSS link of your website content and we'll happily syndicate you on our feed aggregator. Finally, if you're looking to collaborate with us on ESTEST, a great place to begin is simply to use and share your experiences on ESTEST Discovery. We'd love to have developers write translators for their own electronic structure codes because they're the experts, and anyone can develop and maintain their set of plugins for personal use offline or share them back with the community as well. So I thank you for listening and encourage you to visit our websites estest.ucdavis.edu and estest.ucdavis.edu/disc, and I'll happily answer questions now.